Hello everyone, this is DSA Zindabad. Today we are going to solve the 18th question of our virtual DSA sheet and the question is word search. So now let's look at the problem statement. Given an m cross n grid of characters board and a string word, return true if word exists in the grid. The word can be constructed from letters of sequentially adjacent cells where adjacent cells are horizontally or vertically neighboring. The same letter cell may not be used more than once, right? So we'll be given a 2D array, right? Or we can say a matrix. From matrix, we need to find out if there is a word which is present over there in our matrix or not. If present, then we need to return true, otherwise false, right? So now let's look at the example. Let's say this is our matrix, and from this matrix, we need to find out this word, which is A, B, C, C, E, D, right? From there, we can directly say like we have this path A, B, uh, uh, C, C, E, D, right? So we'll directly return true from there, right? So now let's look at the second example also. From this matrix, we need to find out C, right? As we can directly see, C is over there, right? So it will return true. So now let's look at the third example too. From there, we need to find out the word A, B, C, B. As we can directly see, there is no word which can be found over there in the matrix, right? So we'll directly return false, right? So we need to figure out like whether a particular word is there in our matrix or not. If this word is present in our matrix, then we need to return true. Otherwise, we need to return false, right? I hope all of you get what the problem statement is, right? And what we need to figure out, and right. So now let's jump into the approach, how we are going to solve this question. Approach. So for this, we'll be following a simple approach, which is like there is no optimized algorithm, no optimized algorithm for this problem, right? We need to be we need to follow the brute force approach, right? And the for brute force approach, what we'll be using, we use backtracking plus recursion, right? We're gonna use this technique, right? So now let's take an example and we'll try to figure out like how we are going to use this technique in our question, right? So this is our matrix, right? So what we'll be doing, we'll just directly traverse over the entire matrix and we'll try to find out whether we found a particular word or not. And the word we need to find out is A, B, C, C, E, D, right? So from there, like we'll start from the initial element, which is A over there. So after this, what we'll be doing, we'll check for each and every neighbor. So its neighbor will be, let's say, we are at this particular element. So its neighbor will be the upward, the right, and the left neighbor and the down neighbor. We can't go in the diagonals. No diagonals value, no diagonal neighbor, like, right? So what we'll be doing, we'll directly make a call for all of its neighbor and we'll try to check whether the particular element is present there or not. Like initially we are at 0, comma 0, and at 0, comma 0 we'll try to check whether this element is equal to the element of word of 0, right? So from there we can directly see A and this A is similar, right? These both are equal, right? So after this we'll just increment our pointer, and for this what we'll be doing, we'll go for all of its neighbor like in the four directions, right? So first of all, we'll go upwards. As we can see, there is no neighbor over there. So we'll directly return back and we'll go left as well as we'll go down. And from down, we can see S is not equal to the B, right? So we'll not go over there. So when we come to this direction, which is right? So as we can see, B is equal to B. So after this, we'll go in this direction of B. So same thing we'll do for B also, like we'll call for all of its neighbor. But one thing to notice over there, like since we already visited A over there, so we need to keep track of all the visited elements, right? So whenever we visit a particular element, after visiting, like after checking all of its neighbor, what we'll do, we'll directly put a dot over there, put a dot or star to just like keep a track that it's already visited. Like for visited element, we'll mark it with some special symbol, like it can be dot, star, dollar, or anything, right? So after this, like for B, what we'll do, we'll call for all of its neighbor since it is already visited. So this call will not take place, and this call will take place, but there is no element over there. This call will also take place, but F is not equal to the element C, so this call will not happen, right? After this call will take place. Same thing goes for C over there also. Like we'll directly call for all of its neighbor which are in the four direction, right? Same goes for this also, same goes for this, same goes for this. So like we just need to backtrack over there and need to find out whether there is some more path in the entire matrix, right? This is what is called like backtracking, right? I hope this approach is clear to all of you guys. Like what we'll be doing, we'll just backtrack over the entire matrix by, and we'll also keep a check whether this particular element is visited or not, so that we try to dig by doing this, we'll try to reduce the calls, try to reduce number of calls, right? And we'll code this thing with the help of recursion. What recursion is, for recursion we just need to figure out base case, and the rest of the things will be handled by the recursion itself, right? So now let's try to code this thing up so that you guys have a better understanding of like what I'm trying to say, right? So here we are. Initially, we'll take the rows and columns, right? And we'll indicate the number of rows. If n is equal to 0, then we need to return false, right? And int m will be equal to the number of columns, board of 0 dot size, right? After this, if this is the like edge case, if word dot size is 0, right? We need to return false. These all are the edge cases. So after this, let's make a helper function with the help of which we'll make a recursive calls, right? So over there, we'll directly have this, and we'll also have word, and int I and int j will be the index of that particular element, int n, int m, right? And int k here, int k is the length of the word which we need to find out in the entire matrix, right? So this one is the base case which we need to, if we traverse all the entire matrix, and if we find out if k is greater than equal to word dot size, right? Then this means we found the entire word in a matrix, right? So there is one overflow condition also. If I is less than 0, or I is greater than equal to n, or j is less than 0, or j is greater than equal to m, or board I j is equal to the dot. Dot is here for indicating like we already visited this element, right? or word of K is not equal to board of B. Board, board of I, J. Then we just need to return false, right? This one is also the like, this is for the overflow condition, right? So we just need to traverse over this matrix, right? So for traversing over this matrix, we need to have for loops, two for loops, with the help of which we can directly make recursive calls for all of its neighbor, right? For int I equals 0, I less than n, I plus plus, for int j equals 0, j less than m, j plus plus, and if word of 0 is equal to board of I, j, then what we need to do? We need to make call for the helper function. Helper function, board, word, I, j, n, m, and initially k element will be 0, right? If this function returns true, then we need to return true, right? So we'll just traverse over the entire matrix with the help of these two loops, right? So now let's write the recursion part, right? So initially, whenever we get the element, we need to mark it as visited. We can use dot or any special symbol if you want. So initially we'll make bool temp equal to false. So we have four neighbors, right? So for the four neighbors, we'll just make. So what can be the values of like four neighbors? Like whenever we are at the 0, comma 0. So what will be its four neighbor? One can be 0, comma minus 1. Second one can be 0, comma 1. Third one can be minus 1, comma 0. And the fourth one can be 1, comma 0, right? So initially it will have 0, 0, minus 1, and 1, right? And for the y also will have 0, comma minus 1. So for 0, comma minus 1, what do we mean? Like the row will be as it is. These all are up, down, right, and left, right? Minus 1, 1, 0, and 0, right? Let me just write this thing for you so that like, let's say we are at uh, z, it's something like 0, comma 0, right? So 0, comma minus 1, what it will represent? It will represent the same row and the like it will represent the left part, right? Left, left neighbor, you can say. And when we talk about the 0, comma 1, it will represent the right neighbor. When we talk about the minus 1, comma 0, this will represent the upward neighbor. And when we talk about 1, comma 0, this will represent the down neighbor, right? These all are its neighbor, right? So now we'll directly run a for loop I less than equal to 4, I. So over there we have index. So index, right? After this, we'll have a temp, and the temp value will be directly or with the recursive call, and the recursive call will be something like this: helper for each, like let's say we are at this a which is at 0, comma 0. So for this we need to make calls for all of its neighbors. So it will be something like this: b board, right, and word, And this time what we need to do, what we need to pass x of index, right, and j plus y and index, right? Because we need to check for all of its neighbor, like whether we have a different, whether we are getting the path from it, any of its neighbor or not, right? We need to check for each and everything. And m, and we need to increment our k also, right? So after this, board of I comma j will be equal to word of k, right? Now at the end of this, we just need to return temp, whatever will be the value of the temp, we'll directly get the value, right? So now at the end of this, we also need to return false if this condition doesn't hold true. Return false. Now let's try to run this code. There is one typo over there, line number 18, right? There is one comma which is missing over there after n value, right? So now let's try to submit this code. Yeah, this code runs perfectly fine. Now let's discuss the time and space complexity for the same. So here we are. So since this is a, these are the loops which will try to run. So it will require n cross m into number of recursive calls, right? This will be the time complexity, which will be big of n cross m cross x, where x is the number of recursive calls, right? This will be a time complexity. Now we need to figure out this x. Since we need to have four calls, right, for all of its neighbor, right, four neighbors for each and every element, right? So you guys might be thinking like its time complexity will be something like this: big of n cross m cross 4 raised to the power l, where l is length of word, right? But this is not the time complexity for this. The time complexity would be big of n cross m cross 3 raised to the power l. Why 3? Let me just give an example for this. Like let's do a diagram, quick diagram for this example. Like the 3 over there, because in worst case we have to travel till last cell of the matrix, right? And now in the last cell, recursion depth will go as far as 3 raised to the power l. Now why not 4 raised to the power l? Because we never visited the path where we came from. That is the base case. Like we never go back, right? Let me just give you an example for this. Let's take this example. This is, let's say this is our matrix A, B, C, E, A, B. And here we have S, F, C, S, B, C. And here we have A, D, E, E, R, Z. So this is our matrix. And the search word will be A, B, C, C, E, D. So I'll be making initially like recursion tree like for the same. So initially we have nothing. So we'll have A 0, 0, right? And A 0, 4. And for this we'll have AB and AS. And AS, at AS will stop. And for this we'll have AB 1, 4. These are the indices 0, 1, 2, 0, 1, 2, 3, 4, 5, right? AB 1, 4, and we'll have AB, right? So after this, after AB, yeah, after this AB, what we'll have ABC, and we'll also have ABF, and at ABF we need to stop. right? And after like when we encounter ABC, again we need to go for A, B, C, E, and the search word here is the A, B, C, C, E, D, and we also need to calculate A, B, C, C. So at this we need to stop because we didn't find like the fourth C over there, right? Fourth element, which is C over there, right? So after this, we'll again need to A, B, C, C, S, or we have A, B, C, C, F, and again we'll have A, B, C, C, E, right? What do I mean? Like, let's say we have this A, B, C, C. Till now we will find this, right? So what are its neighbors? Its neighbor will be F, E, and S. So we need to traverse for all of its neighbor, right? So after this, its value will be like, since this is not the required part, this is also not the required part, this is the required part. So again, we need to make a call A, B, C, C, E, and E. Or either we have A, B, C, C, E, D. At this, we need to stop and well, the word is found over there. The word is this one, right? So now let's go upwards and make the calls for the remaining part, right? At AB 1 comma 4, what we'll have ABS, and we have ABR, and we have ABC, right? And as you can see, like at any level, we have at max, we have at max three calls. Like, what do I mean by three calls? Like, uh, at max, there are three directions because one direction is the that direction in which we came from. So there is no need to traverse over that direction in which we came from. That is, this one is the base case. Remember, like I told you guys, like we try to reduce the number of calls by making the element to be visited, right? That's the reason over there. So I hope all of you get like why the time complexity should be big of n cross m cross 3 cross l instead of this one. And when we talk about the space complexity, so for this, the space complexity is constant since we are not using any extra space, big of 1. As you can see, like from the code itself, there is no extra space which we'll be using. So no extra space, no extra space, right? I hope this approach is clear to all of you guys and the time complexity too. Just try to do a dry run with the help of pen and paper, and this question will be quite easy for you guys once you do a dry run by yourself, right? Thank you so much for viewing the video till the end. Please like, share, subscribe, and comment if you have any doubt. Thank you so much.